Hi, you're listening to Defend Your Time, brought to you by Ontinue. I'm your host, Chris Taylor. This is the podcast where we help you get stronger security, more value, and fewer headaches out of your Microsoft security investments. And today, I'm joined by Iris Safaka to talk to us about Agentic AI applied to security operations. This is the second episode in a multi-episode series we're doing on Agentic AI applied to SecOps. Iris leads the data science team. She's the lead data scientist here at Ontinue. She runs the AI team. She's been working at the intersection of security and machine learning and AI for the past 15 years. Iris holds a PhD from the Swiss Federal Institute of Technology at Lausanne. Iris, thank you so much for being here today.
Hello, I'm very happy to be with you. Hi, Chris.
In our last episode, we spoke to Toyas Hausman, who is the Chief Technology Officer at Ontinue. In that conversation, Toyas talked to us about the expanding gap between vulnerability and complexity in cybersecurity and the capacity of the overall security workforce. We talked about the evolution from deterministic to AI assisted, all the way to agentic AI. And today, Iris is going to help demystify that. So the topic of our conversation today is demystifying agentic AI for SecOps. Iris, my first question for you is, what are AI agents?
Yeah, that's a very good question. Thanks, Chris. So let's start with some definitions indeed. So the adjective agentic, or having agency, describes a system that is able to make independent decisions in pursuit of a goal. And agents, it's not a new concept in artificial intelligence. They have actually appeared back in the 1960s. They proliferated in the 80s and 90s, and they enjoyed quite some success in the beginning. So the systems were programmed to emulate the decision-making ability of human experts by leveraging large bodies of human knowledge encoded into a series of rules. They created a lot of optimism, but indeed some inherent limitations and disadvantages. They had those systems, never allowed them to deliver the initial promise and expectations, something we see maybe happening in our days. So the main disadvantages of those systems were two. First, what we call knowledge acquisition problem. And essentially that means it is very difficult to obtain the expert knowledge in terms of rules. It's very laborious, a very tedious task, right? The second limitation of those early AI systems, as expert systems, is their performance. Simple computational tasks could end up being very time and resource consuming. Now, let's forward to recent years where we have witnessed a tremendous advancement in many aspects in the domain of AI, the most prominent among those being the appearance of transformer deep learning architecture, introduced initially by Google, which allowed researchers and people around the world to actually train large language models on huge data sets and effectively encode vast amount of human knowledge within only one model. It was a great success when we compared to what was happening back in the 80s and 90s, where human experts had actually to encode all this knowledge by hand. Then, of course, we saw the GPT models coming into the picture, the generative pre-trained transformer, these LLMs introduced by OpenAI, and of course, followed by other foundational models like Claude, Mistral, Llama, and eventually the whole Gen AI discipline, just for some history. Now, today, when we refer to an autonomous AI agent, we refer to a system that essentially uses sophisticated reasoning and iterative planning to autonomously solve a very complex multi-step problem. Yeah, the agents can execute tasks, they can take decisions, and that is all being done without requiring any direct human intervention. When we talk about sophisticated reasoning, that certainly implies using foundational models in the heart of the system, LLMs, to achieve an objective, but not only that, as we will explain further today.
Okay, so that's extremely helpful background. So what are the basic properties of an AI agent?
Yeah, that's an important topic. It's essential to know that AI agents have some properties that differentiate them when we compare them to conventional generative AI applications. First of all, an AI agent is a system that is given an objective to achieve, contrary to any classic enterprise application where we need to gather the requirements, clearly define the code and the business logic that needs to be created. An AI agent is only given a high-level objective, but not a coded logic, how to reach this objective. It will use reasoning, planning, and tools that it possesses, as we will also see later. We can go into deep explaining this concept a bit later in order to achieve their goals. The second important property is that an AI agent is able to leverage sensory inputs to make sense of their environment. This could be text, knowledge, image, video, anything really. And it also has the ability to use advanced algorithms to not only analyze these inputs, but also to plan and execute actions towards achieving this goal. The important property to note about the systems is that they are able to respond to dynamic scenarios. And that means essentially that when conditions around them change, the AI agents can adapt their behavior. They can replan again, continue their execution based on previous executed plans. And they can also learn from what they observe. They can also learn and optimize their behavior through feedback and reward functions. Finally, an agent can execute actions in real time, and usually it should not require any human approval for this.
Okay, this is really helpful. So the way you would differentiate an AI agent from just maybe what I might think of as a generative AI model is it's got a clear objective that can be a complicated long-term objective or multi-step objective. It takes in its different sensory inputs, and that can be lots of different types of data or media. And then they can apply the algorithm through reasoning, planning, adapting, self-reflection. How do you go about building an autonomous AI agent?
Yeah, of course, it will take having some foundational models to use, but that's not only it, right? Generative AI has enjoyed a huge success in the past year. As we saw in many companies, including Ontinue, we have been able to successfully develop Gen AI applications in different business functions to solve some very difficult problems. But despite this early success, it also became obvious that when it comes to LLMs and Gen AI applications, there are certain limitations related to reasoning and more complex problem solving. Even though, as we speak, those limitations get more and more addressed by very recent powerful models such as O3 from OpenAI, R1 from DeepSeek, and we will keep seeing LLMs and the foundational models become better in reasoning. But just to go back, at some point, we all practitioners started realizing and noticing that by applying certain strategies that resemble a bit how we humans and think and function, these studies could significantly improve the performance of the basic LLMs. Now, we came up with some design principles that today we refer to as agentic AI design principles. Essentially, for building an AI agent, applying those design principles is important. And it's very important to make sure we can create an agent that has the properties we discussed just before. I have to note also here that there are many frameworks that appeared recently that can streamline the development on agentic AI workflows, as we also call them, some of them being LangGraph, AutoGen, Crew AI, and the list grows longer every day.
Okay, that makes sense. So can you walk us through some of these agentic AI design principles?
Yeah, certainly. So let's talk about reflection. So as of today, we humans are quite used to interact in one-shot mode with our favorite LLM in a more of QA mode, right? So we ask a question, we expect an answer. And when we don't like the answer to our question, we often manually prompt the model to correct and criticize its own output. And we have seen that this often results into better answers. So I don't know, Chris, what is your favorite LLM to use? Imagine you use your favorite
Copilot.
LLM,
I'll use
Copilot.
Copilot. Yeah.
All right. So imagine you ask Copilot to write an essay about your favorite topic. Tell me, what is your favorite topic?
The band Fish, rock and roll music. Yeah.
All right. Okay, so it is certainly capable of doing so. It can start typing an essay till it finishes, from the beginning till the end. right? But what happens most of the time, you might say, hey, can you please summarize the insights in the first paragraph? Can you maybe check your facts in the second paragraph, etc., etc.? So reflection is, in the end, about automating this type of self-criticism to the LLM. This function can cause the model to spot its own problems and come up with a constructive suggestions to itself. And
Does
actually,
this help with hallucination?
yeah, certainly does. Right?
Okay.
And you can make sure to even reduce further hallucinations. You can go beyond relying on the inherent abilities of the LLM to improve itself. You can also provide it with tools to help it evaluate its own output. For example, imagine we give your favorite LLM copilot a search tool that we can prompt it to use for fact checking. So if I had to summarize, there are three elements to remember here when we talk about reflection. Uh, First, we automate the self-criticism process. Second, we prompt the model to spot its own errors. Third, we give it access to additional resources to correct its own errors. And in that way, the model can examine its own work and come up with nice ways to improve it.
Okay. So this is helpful. So you've talked about reflection. Reflection would be the first design principle. What's next?
Next is a tool usage. This is a pattern that we have been already applying for conventional generative AIs. We touched upon it already when we talked about reflection. So LLMs can be fine-tuned or even better prompted to use tools with detailed descriptions of their functions. So imagine some tools like a web search tool that can execute queries, it can send emails, or even schedule Teams meeting, right? This tool list needs to be available, included to the LLM. We can send this every time in the context, but it can also include hundreds of tools. Just think of all the number of APIs available within an organization. Okay, there exist heuristics, how to pick a handful and relevant tools for each task, like applying RAG. In the end, tool usage is about providing relevant tools and letting an LLM decide on which one to use. First step, provide a list of relevant tools and their descriptions. Second, prompt the model to match tasks with available tools. And third, enable the whole system to execute tool calling and consume tool output so it can reason and continue further its pursuit of achieving a specific goal.
Okay, so it's the agent can now reflect on its own performance, self-critique, and make itself better, and it has access to a whole host of different tools. Okay, what's
Next is planning, right? It's an essential component of building efficiently and effectively AI agents. And planning is about enable the model, a system to come up with and execute a multi-step plan to achieve its objective. Okay. Many complex tasks can be done in a single step. I think you agree with me, or just using a single tool. This goes to humans ourselves, right? We usually, when we have to solve a complex problem, we create iterative workflows in our minds. And this is what an LLM could be programmed to do. So in our previous example, you could think of, instead of asking Copilot to create an essay on your favorite topic, you can ask it first to create a skeleton of the essay, maybe start putting some bullets. But you can also prompt it to decompose this complex task into simpler and actionable steps. That's what this planning, coding, this planning capability is about. So step number one, let the model autonomously decide on what steps to take to accomplish a high level objective. Step number two, prompt it to decompose this complex task into simpler steps that it can use tools to actually execute. Uh, Now, an important point here is the following. Again, for us, the humans, very complex tasks, we cannot ahead of time decompose them into simpler steps, right? In the same way, we should also let the model dynamically produce the next step based on intermediate results. This is what we call reflect and improve strategy, and it has proven to help a lot the model to efficiently plan its own work.
okay, this is fascinating. It's a little bit scary, but okay, so the tool can reflect and self-correct and self-critique. It has access to all of the different tools that might be available through APIs. And now it has planning and reasoning. What's the final of your four design principles here?
Yeah, a core design principle when we talk to agentic AI is multi-agent collaboration. And for explaining this pattern, I will start with two key observations. First, prompting an LLM to play a specific role can highly influence its quality output. We observe it every time. For example, we ask an LLM to respond using a specific style, like a CISO, or you can also make it talk like a pirate, etc., etc. It does it very well. So the role definition certainly helps, and it goes into the context through the system prompt, but even if the LLM can accept long context, their ability to understand all of it is limited. So if we start pushing too much context, it will not focus. So having small, well-defined context, make them focus on the instruction they're given, and hence they can become more effective on their task. So in a nutshell, when we talk about multi-agent collaboration, this is about having different models, different agents solve different parts of the same complex task. We prompt its model to adopt a specific role, and we also give it the tools and resources based on their role. Fourth, we let them collaborate. In that way, many models can work independently on the same complex problem. They split up tasks, they debate ideas, and they produce a better solution than a single model would do in the end.
Okay, fascinating. Okay, so I'm thinking about an AI agent as one entity, but in the same way that it can split up the tasks, a complex objective into discrete tasks, it can also split itself up into unique roles that can focus on a specific context and then collaborate with each other to accomplish the entire objective.
That's right. That's how also we humans work, right? We don't try to solve everything at once. We have different roles within an organization. We have different capabilities, and
Right.
we try to solve it all together.
Okay, this is amazing. So then how do you apply this agentic AI with these design principles to security operations, let's say security incident investigation?
Mhm. Okay, so before LLMs and all these agentic frameworks, if you really wanted to create a program that automated the work of tier one and tier two SOC analysts, you would essentially have to write down a huge static set of rules that is keep changing for the program to follow for its investigation, to make back the connection with expert systems of the 70s, right? This is a huge, tedious, and laborious task. However, security incident is not a static problem, and each case is very different. Every customer environment is unique. The threat landscape is constantly changing every day, and one cannot simply use a boilerplate of predefined security checks, a runbook that fits all to perform an investigation. We need to be flexible, adaptive for each unique use case. But now, with LLMs and agentic AI patterns, as we saw before, we can introduce this necessary flexibility and planning that is needed to conduct an end-to-end security incident investigation automatically. And that's great news.
And how do we do this at Ontinue?
So at Ontinue, we have built an AI agent for this purpose, for automatic incident investigation. We have leveraged, of course, the powerful foundational models, LLM, and the agentic patterns we described. We use the system to investigate every escaped incident. This is every incident that has not been auto-closed by deterministic automation and needs to be further investigated by a human. So it works like that. So for those incidents, we let the autonomous system generate iteratively an investigation plan, and we let it execute automatically all the steps of this plan. At the end of this process, the system assesses what is happening, the situation, it summarizes into key findings and into a report, and it makes available this report into our Defenders Workbench, which is the internal tool we use at Ontinue, in order to help bootstrap the human-led effort. And we have seen that it really reduces dramatically the time to respond, the time to close each unique use case.
Can you share what is the secret sauce here? How are we able to do this so well?
Yeah, okay. There are three key factors here. First of all, we talked extensively about tool usage. And yeah, Ontinue, we have an arsenal of those tools that we develop in-house and can allow us to perform very fine-grained security checks on demand. This is because we have deep integration into our customers' environment. And this fact allows the investigator to use a multitude of data sources and logs and get deep insights during investigation time. Based on these insights, it can plan, replan, till it reaches an assessment about what is going on. Second important topic is that we leverage past knowledge. Our security experts, SOCs T1, T2, have triaged thousands and thousands of incidents in the past. This is not lost knowledge. This is actually an extremely valuable data source, which is unique for each customer environment. We do store and process and leverage all this knowledge for the autonomous investigation to learn and get inspired on how to plan an investigation, how to form a hypothesis in the same way that human analysts do, how to conclude based on key findings, and so on and so forth. Last but not least, I'm going back to our experts. Again, expert feedback. Our security experts are providing constantly feedback on the quality, on the findings, on the planning, and the overall reasoning capability of the system. This is feedback we capture real time, we store, we operationalize, and we use continuously to make the system learn and adapt and optimize its behavior based on this valuable human expertise that we have within Ontinue.
Iris, thank you so much. This is such an exciting topic, and I feel like you've explained this so well. I feel like I got a master class in what's happening with agentic AI, and what a great use case to apply this to solve a real problem.
Yeah, this is really exciting, actually. It's very exciting times to work in the domain of security operations and AI. This is the first time we can see those systems actually providing value for the very difficult problem of incident triage. With these advancements, we're helping more and more our SOC experts to do their job faster without having them burned out, without looking over and over big amounts of data sets, doing repetitive jobs, etc. We leave the autonomous investigator do the job for them.
Okay, something I like to ask podcast guests, when you're not building agentic AI agents to solve cybersecurity's biggest challenges, what do you like to do with your free time?
Oh, that's a good question. Before having kids, I like skiing and playing tennis. Now, most of my time I'm spending playing board games with my kids.
Oh, that's fun too. Okay, thank you, Iris. I really appreciate your time today. Thank you for listening. This is Defend Your Time, the podcast where we try to help you get stronger security, more value, and fewer headaches out of your Microsoft security investments. This was the second in our multi-part series on agentic AI applied to security operations. Iris, this was a real pleasure. Thank you again so much for your time today.